Hello and welcome to Anton Math. Now in this video we're going to be starting off our conversation about basic probability, and we're going to be using a lot of what we talked about in part 5. So if you haven't watched the videos in part 5 yet, make sure to go back and watch those, particularly everything about experiments and events, about counting the orders of sets, and also just about counting in general with our choice function and our permutation function. We're going to be using all of that here in these next several videos when we talk about probability. Now this is the first video, so of course, as per usual, I need to start off with a bunch of definitions and terminology. So we write P of E to denote the probability that an event E occurs. So P of E is going to be a function. P is the function, E is going to be the input of the function, where E is some event of an experiment. Now probabilities of 1 and 0 correspond to absolute certainty and impossibility respectively. So remember before when we were talking about events, we said if we had a sample space S, when we talk about a sample space S as an event, we said it was certain, and when we talked about the subset of S, namely the empty set, we said that was impossible. So probabilities 1 and 0 are going to basically correspond to events that are the entire sample space, and events that don't have any of the sample points in the sample space in them. Now we say that a list of all the probabilities of all the outcomes of an experiment is called the probability distribution of the experiment. And in the case that each possible outcome is equally likely, for example a coin flip or a die roll, the probability distribution is called uniform. So in this video we're going to be talking about uniform probabilities and uniform experiments. Now if a uniform experiment has a sample space with n elements, then we assign the probability of 1 over n to each outcome. So for example, for a coin flip, right, we can do an example here. We know a coin flip is a uniform distribution, right? There are two sample points, heads and tails, and each of those sample points is equally likely to each other, right? I have an equal chance to get a heads and a tails. So I know that the probability of heads, and here I'm using heads as a sample point, but you could also think of this as the event that only contains heads, or the probability of tails are both equal to 1/2, 1 over n, right? My sample space is size 2, it has a heads and a tails, so the probability of each flip is 1/2. We knew that already, right? But this is just a basic example. Now if a uniform experiment has a sample space S, then an event E will occur if the outcome is one of the order of E outcomes in E. So this is when we're looking at, here the coin flip, the events only had one sample point in it, so each sample point had a 1 over n probability. But if we have an event E with more than one sample point in it, then we need to know how to calculate that probability. Now we expect that E will occur in the order of E out of the order of S of cases, right? If the event is both uniform and if it's repeated. So we define the probability of E to be the order of E over the order of S, again where S is my sample space. Now this only works with a uniform probability, and we'll get into non-uniform probabilities in the next section. In some situations you're going to have sample points that have a different likelihood than other sample points. So we can't just count how many sample points they are to find the probability. But in a uniform environment, we can absolutely do that. So let me take this all away and we'll look at an example. So example, a fair die is rolled. SI is the event that the number I is rolled for I 1, 2, 3, 4, 5, 6. So here I'm using an index notation, right? So we know that I'm saying S1 is the event that a 1 is rolled, S2 is the event that a 2 is rolled, S3 the event that a 3 is rolled, and so on. So we have 6 events SI. E is the event where the roll is odd, and F is the event where the roll is less than 3. And we want to find the probability of these events. Now, because this is uniform, the probability of my SI, they're all the same, right? Each of my SI only has one element in it, so there's going to be the order, which is 1, over the order of the sample space, which is 6. So for any I, it's going to be 1, 6. So I wrote it in general, PSI for all I's, but this would be the same as writing PS1 is 1/6, PS2 is 1/6, etc. The probability of getting any individual roll is going to be 1/6. Now the probability of E, as we just discussed, because we're rolling a die, this is a uniform experiment, so all I need to do is look at the order of E divided by the order of S. Every event in E is equally likely to all the events in S, so I just need to know how many events there are, or how many sample points there are in E. Right? Now the roll is odd, means that 1, 3, or 5 is rolled, so I have 3 sample points in E. There's 6 sample points in my sample space, so the probability that an odd number was rolled is 1/2. Now finally looking at F, F is that the roll is less than 3, so I'm going to be looking at the order of F over the order of S. The roll is less than 3 means that the roll is 1 or 2, so there's 2 sample points in F, 6 sample points in S, so the probability that the roll is less than 3 is 1/3. Now one little other property I want to mention here. Well, first of all, whenever we're dealing with uniform experiments, you'll notice that all of my solutions here were proper fractions. And in general, when we're dealing with uniform experiments, we're going to have proper fractions as our probabilities. It's going to be very nice, and we'll see all our answers are going to work out very well. But one more thing, when we're dealing with multiple events, let's say I have these 2 events, E and F. Let's say they're disjoint. Then from our conversation in part 5, I know that the order of E union F is equal to the order of E plus the order of F. Right now, in general, this would be the order of E plus order of F minus the intersection of E and F. But because they're disjoint, another word for disjoint is mutually exclusive, right? We've talked about that before. Because they're disjoint, the intersection is empty. They don't have any elements in common, so the minus intersection is just minus 0, so we don't even have to worry about it. So then the probability of E union F, and in a practical setting, we would look at E union F to look at the probability of E or F. That's really what we're doing here. So up here, for example, I could say the probability that the roll is odd or less than 3 would be the probability of E union F. Well, that's just going to be the order of E union F, which is the order of E, plus the order of F, divided by the order of S. Right? I'm really just plugging in order of E union F as a single event up here, but we found it to be E plus F. Well, I can break this up. This is order of E over order of S, plus order of F over order of S, which is just probability of E plus probability of F. So if we have 2 disjoint events, the probability that one or the other of those events will happen is simply the sum of the probabilities of each event. Now, I can't use E and F up here as an example because they're not disjoint, right? They both share the sample point 1, so it doesn't really work here. But I could do, for example, the probability of F or S5, let's say, right? So this is just saying the probability that the roll is less than 3 or is equal to 5. Well, this is just 1/3 plus 1/6, because those are the respective probabilities of F and S5, which is equal to 1/2. I'll let you do that little calculation on your own. Okay, so that's an example. And just one more definition I want to go over before we move on to the next video, which is non-uniform probability. So let's consider an experiment with sample space S equals S1, S2, all the way to Sn, so the sample space has a size n. Then a probability distribution for the experiment is a function p with the following properties. The first property is that for each Si, or in other words, for each sample point in my experiment, I have that, well, first of all, I is between 1 and n. I have that the probability of Si is a real number, and it always lies between 0 or 1. Probabilities in general are always between 0 and 1. This is how we kind of define probabilities. Remember, we said 1 is a certainty and 0 is an impossibility. So once you go above 1, it doesn't really make sense. It's not more certain. It's just as certain as if it was 1. So the probability of something happening is 1, and it's never going to be higher than that. And also, we can't, if we talk about a cumulative probability of everything in our distribution, that's not going to be more than 1 either. So in particular, if I look at all of my sample points and take the probabilities and add them all together, so let's take the probability of S1 plus the probability of S2 plus the probability all the way to the probability of Sn, this is going to equal, and I could write this as a sum. Let's go ahead and practice our sum notation. So I from 1 to n, probability of little si. This is always going to equal 1. So in other words, if I take every sample point in my sample space, the sum of the probabilities of all those sample points will always be 1, because the probability of one of them happening is 1, right? Okay, that's it for uniform experiments. So we're going to look in the next video at non-uniform experiments, where the sample points don't have the same probability, and figure out how we can break that down into a uniform environment that we can solve out the probability. So we'll see you there.